let me complete something which needs to be said, because as formulated, some of the propositions about iterated deletion of strategies, they are not correct. Simply, it's something which people usually assume, and that is that we delete always a finite number of strategies. So, well, often people just on an introductory course work with finite games, so there exist finitely many strategies to begin with. But even if you don't work with a finite game, sometimes people define the deletion process as a finite chain of deletion of strategies. Now we have defined it by allowing to delete any number of strategies at a stage, and therefore, despite that the chain is in the definition as is finite, we do allow to delete at one step from s t minus 1 to t any number of strategies, and that's not what is sought in the proposition. So we need to make them precise. We work only with deletion of finitely many strategies, and let me just show this. Let me be precise now. So the first fix is that iterated elimination of finitely many, it's important, strictly dominated strategies does not change the set of mixed Nash equilibria. So it's important to demand that there will be finitely many such strategies. And the proof, which goes by induction, uses that. So it starts with deleting a strategy, and then inductively it can work for any finitely many number. By the way, another thing which I want to add is this corollary, and that's that if we iteratively eliminate finitely many strictly dominated strategies, and we end up with a single strategy profile, then, since we have not changed the set of the Nash equilibria, that profile eventually is the only mixed Nash equilibria, and by the proposition, which we have proven for finitely many deletions, that's also the set of mixed Nash equilibria original. So these are all the mixed Nash equilibria. Next, we saw that for deleting weakly dominated strategies, some mixed Nash equilibria might disappear, and then we said that it is always true, so that the no Nash equilibria appear. But that's also important to note that it's also important to say here that it's finitely many, because also we proved for one, and then we said by induction it can be shown for any finitely many number of strategies. First of all, we also derive a similar corollary to what we saw before, and that's if we iteratively eliminate finitely many weakly dominated strategies and are left with a single profile, then since eventually it's a Nash equilibrium, it's a mix, but a Nash equilibrium, and we have not added equilibria, as we have proven, because we have deleted finitely many weakly dominant strategies, it also has to be a Nash equilibrium of the original. So here the Nash equilibrium of the original. Game. Now, neither this corollary, and definitely not a proposition, does not hold in general if we allow for deleting infinitely many strategies, even if those are strictly dominant. So even by deleting infinitely many strictly dominant strategies, we can get a new equilibrium. And then, so we just proved that basically this corollary doesn't hold. We showed an example why it doesn't. So this is an example which you have seen on the tutorial, and there the arguments about the equilibria do not follow from the arguments about deletion of the strictly dominating strategies. So please review the solutions for the second tutorial, which we've seen today. I've fixed it. So, iterated elimination of infinitely many strictly dominated strategies, even strictly dominated, may introduce new mixed Nash equilibria. And we show basically that this corollary fails to hold. So consider the game, the following game, similar to what we, not the same, but similar to what we saw in the tutorial. And that's two players, strategy set, half open segment 0, 1, half open interval 0, 1, open at 0, close at 1, so including 1. It means. And the utility function is simple. If both x and 1 are 1, then both players get 1, get 1 half. Otherwise, they just get the product x times 1. Now here, any strategy, let's start with the first player, it's the same. With the first player, it's the same for both players. Is any strategy between 0 and 1 is, as before, strictly dominated. For example, if you just take anything between that and 1, for example, that plus 1 divided by 2. And analogously for player 2. So we can just delete all those in one move, in one deletion. After deleting all those strategies for both players, we will be left with the single strategy profile 1-1. But it will not be, it's because in the game which we get with one strategy profile, it's the only Nash equilibrium. And it's also the only mixed Nash equilibrium, and that's the only thing we have. But it's not a Nash equilibrium originally. And that's the counterexample. Because, for example, player 1, any player actually can improve by deviating to anything which is larger than half. Because for 1-1 it gets half here, and if it deviates to 3/4, then it gets 3/4 times 1, 3/4. So important to remember that when you have to delete infinitely many strategies which are strictly dominated, it doesn't work what we prove. Please note that it does work that if we delete a finite number of strategies from infinitely many which we could have deleted. But we have to delete finitely many in order to have those conclusions which we like. So it's always important to remember. Okay, that's basically the important addition. I think again that's a bit too advanced maybe for a beginning course, but it's nice that you will be able to understand this stuff. So in books, I think they usually define the deletion itself as a finite process, and the process is always that you delete strategy by strategy, not like we said that we just delete something. So maybe I should have defined deletion to be finite, but I think it's still important to basically understand this stuff.